This video analyses a simple fold on a geological map. So when faced with a map like this, the important thing is to try and understand the topography, because of course the topography as well as the structure will control the outcrop pattern. So we're fortunate on this map because we've got topographic contours, and we can see we've got the 100-metre contour here, the 200, and then the 300, finally the 400. So this is low ground going up to high ground. In other words, there's a valley, or even a pair of valleys that come down through here. So this is a valley side. Well, I can see that the geological boundaries here are running parallel to the topographic contours, at least for these segments here. The top here and the base of the green, that's the top because it's higher on the hillside, this is lower on the hillside. We can see they follow the topographic contours. The 300-metre topographic contour never crosses out of this green unit, at least in this part. And we can see over on this side of the valley, the same thing's occurring. The green unit straddles the 300-metre topographic contour. So this means that the light green material here is essentially horizontal. Now, as we come to this part of the map, we can see that the green unit crosses the topographic contours. The edge on this side, on the eastern side of the map, runs right across the 200-metre topographic contour, and we can see that this side here, over on the western side of the green unit, also runs right across the contours, not just the 200 but also the 300-metre contour in several places. So here, the geological boundaries are clearly very steep. So we have a structure that means it's basically horizontal over here and then tips up to be steep in this area here. In other words, we've got a fold structure. And that fold has a hinged line, or a series of hinge lines, running somewhere like this, so the rocks can be rolled over in that sort of fashion. Well, our mission is to add a bit of precision to that type of qualitative description and try and trace out the hinge lines and the fold axial surface, or at least the axial trace, and then construct the fold axial surface on the map. So let's remind ourselves as to what these things are. So for folded units like this, the hinge line is a line that connects points of maximum curvature for a single layer on an individual fold. So each layer has got its own fold hinge line. If you join these hinge lines together, we create a surface defined by all the individual hinge lines, and this is the fold axial surface. On maps, what we look for is the axial trace, which is the intersection of the fold axial surface with the landscape. And because the fold axial surface is a plane, it will interact with topography, veering in and out of valleys, and we can use that relationship with the topography to define the orientation of the fold axial surface in 3 dimensions. So let's have a go. So as we saw, this layer is coming along and then going steep across the valley in this position here. And the point where that changes is just here. So that's a hinge point. And as we come across the valley to the other side, we can see the opposite occurring, go off these steep beds where the boundary crosses the contours to where it runs parallel. So that is another hinge point on a fold hinge that's running something like that across the valley. We can do the same now for the top of this green layer and trace it along where it's horizontal, and as we go around this corner it's very steeply dipping, crossing the topographic contours, and that inflection there is where the change occurs, so that is a hinge point. Find another one on the other side here, so this is another hinge line running like that. 2 hinge lines, part of the same fold, 1 hinge line here for the top of our unit and another one here for the base. Finally, we can come to this material here, which is coloured in this sort of teal colour, running along here. The geological boundary is running parallel to the contours. Here it's running across the valley. Here it's running parallel to the topographic contours. So we've got a couple of hinge points here and here, another hinge line which runs across like this. So effectively, we can say we've got a hinge line here, a hinge line here, another hinge line here. So our fold axial surface is going to come down in this sort of orientation, capturing these three hinge lines. They're at different elevations. So we're going to draw in the axial trace now, which is a question of simply joining up the dots. So the hinge line here is part of an axial surface that comes down something like this to join into this position. And I'll just do the same on this side of the valley here, coming down like this. So those are two parts of an axial trace, which is the outcrop pattern the axial surface makes on the plane of the map. Now you might be tempted to think that this here is part of our fold structure, but actually this is just a topographic effect. This is the V in the valley as our boundary on the edge of this teal coloured unit wraps around the valley and out the other side, and is simply explained by a horizontal plane coming in like this. So our boundary that is the axial trace is going to come across here something like that. Now we can draw some structure contours on it. And it's just like any other plane. So here's the 200 meter topographic contour intersecting the axial trace, and we can find it again over here. So there's a structure contour coming through like that. That's a structure contour of value 200 meters. There's another one here. Like that, which will be the 300 meter structure contour, and there'll be another one down in here, which will be the 100 meter structure contour on the axial surface, picked out where the axial trace intersects various topographic contours. Well, I can see the trend of the structure contours here is effectively north-south, so the strike of our fold axial surface will be north-south, so something like 0, 0, 0, and the amount of dip on it could be calculated trigonometrically by just using the spacing of the structure contours. Well, we can use this simple trigonometry to work out the dip of our fold axial surface. I've just plotted up the change elevation on this little cartoon. So this structure contour 300 meters, this one here 100, that's our change elevation h, and it occurs across this horizontal distance here, d. So the dip we want to find alpha is, well, the tangent of alpha is simply the change elevation h divided by d. So let's just measure how far that is. I'm just going to take this distance here that we've got from our scale, that's 100 meters. So we're looking at something like, that's 100 to there. That little bit there is the extra bit. Let's come back to this. It's probably what, about 140 meters. So D is 140, H is 100 from 300, which is 200. So the tangent of alpha is equal to that. Well, that's equal to 1.43, and the arc tangent of 1.43 alpha is equal to 55 degrees. So our orientation of this axial surface has a strike of 0, 0, 0, or north-south, a dip of 55 degrees towards the east. There we go. So that's the fold axial surface. As to the fold hinge lines, let's just draw on our hinge lines. We put those on before from 2 hinge points. So let's draw this one on. It's going to come through like this. That also has got a trend of about 000, and I can see on there that the change in elevation, well, there's no change in elevation. It's essentially a horizontal line. So our hinges are essentially 0, 0, that's no plunge at all, on a trend of 0, which is north. So, and of course that would be correct, because if the hinge has got no plunge on it, it means that it's running parallel to the strike of the axial surface, so the trends will be the same. So here's our analysis of the map. We identified some fold closures from the map pattern. We've identified those. We've seen other features on the map that are related to topography. For example, this loop here, which is not part of the fold structure. We've identified hinges as a series of hinge points in here, and we've then joined these up to create an axial trace, which is the outcrop expression of the fold axial surface. We do structure contours on this to define its orientation, which tells us the strike and the dip, and we calculated the dip using some simple trigonometry. So an analysis of a map pattern of a fold with topographic information.